Okay, now we'll start the new topic, which is root locus. Okay, now you already know the previous sessions and basics of the subject. Now what are the roots? The roots is nothing but a numerator polynomial roots are available, and denominator polynomial roots are also available. But which is important, you know that the numerator polynomial roots is nothing but zeros, and the denominator polynomial roots are nothing but the poles. But the system behavior is completely depends upon the poles location and a poles characteristics, am I not? So this roots is nothing but, here the roots are nothing but closed loop poles. This locus is nothing but, the root is closed loop poles, locus is nothing but movement. Now the closed loop poles movement, the closed loop poles movement are a closed loop poles path. The closed loop poles movement or a closed loop poles path is nothing but the root locus. Understand or not? The root locus is nothing but movement of the closed loop poles. But with our basic knowledge, you know that the open loop pole is at one particular location, and its corresponding closed loop poles, after having a feedback, the location may be changed. Let us assume this is at one location and the closed loop pole is at another location, open loop pole is at one location. Now those two locations are different because in closed loop control system there is a feedback. Because of that feedback, the closed loop pole location is changing. But what is, it is changed, but it is a fixed location. But what is the root locus is saying? The root locus is saying that the movement of the closed loop pole, how the closed loop poles are moving. If the closed loop poles are moving, that movement, that path is nothing but the root locus. So if you want to move the closed loop poles, so here is the example I will take. Now this is G of S, which is equal to K by S. This is G of S, open loop transformation. What is the characteristic equation? The characteristic equation, which is nothing but 1 plus G of S is equal to 0. Therefore, S plus K is equal to 0. Therefore, S equal to minus K. This is the closed loop pole. Now, S plus K equal 0. S equal to minus K. This is the closed loop pole, which is a function of system gain K. Now, this is the closed loop pole, which is a function of system gain K. This is the closed loop pole, which is a function of system gain K. Now, when K is changing, when the system gain K is changes, now see here. Now, when K equal to 0, closed loop pole is at, when K equal to 0, closed loop pole is at origin. When K equal to 1, closed loop pole is at minus 1. When K equal to 2, closed loop pole is at minus 2, minus 3, minus 4, and so on. When K equal to infinity, closed loop pole is at minus infinity. Now when K equal to infinity, closed loop pole is at minus infinity. Now if you observe, the closed loop pole location is changing or not? At origin, at minus 1, at minus 2, at minus 3, at minus 4. Now this is the movement of the closed loop pole. This is the movement of the closed loop pole. Now this is the movement of the closed loop pole. Now the movement of the closed loop pole. The closed loop poles are moving, am I not? Now the root locus is nothing but movement of the closed loop pole. Now this direction indicate, this is the direction, this direction indicate, in this particular direction the closed loop poles are moving. Okay, now this is the direction of the closed loop poles movement. That direction will give the two statements for us. One statement is, now this is the direction, now in this particular direction the closed loop poles are moving, and in this particular direction the system gain K is changing from 0 to infinity. Understand or not? When the system gain K is changing from 0 to infinity, then the closed loop poles are moving. Now that movement is nothing but the root locus. So what is the definition of root locus? Now you cannot say the closed loop pole moment. The root locus definition, now you can say the root locus definition is nothing but moment of the closed loop pole when the system gain k is varied from 0 to infinity. When the system gain k is varied from 0 to infinity, then the closed loop poles are moving. Now that movement, that path is nothing but the root locus diagram. So if you want to move the closed loop pole, the closed loop pole must be a system parameter is called as system gain k. Understand or not? Now this is the relation. Now this is the system gain k and this is the closed loop pole which is function of system gain k. So we can easily judge that when k equals 0, closed loop pole is at origin, k equal to 1, closed loop pole is at -1, k equal to 2, closed loop pole is at -2, k equal to 3, closed loop pole is at -3, and k equal to infinity, closed loop pole is at -infinity. Now the system gain k is changing from 0 to infinity, the closed loop poles are moving, that movement, that path is nothing but the root locus. So note down the students the definition of root locus. The root locus is nothing but the movement of the closed loop poles when the system gain k is varied from 0 to infinity. Okay? Note down this. Okay. Now in that way you can easily find the closed loop control system, closed loop poles movement. Now if that is an easy one, now can you please do it for this? K by s power 5 plus 8s power 4 plus 3s cube plus 2s square plus 5s. This is the open loop transfer function. Now I want the characteristic equation. Now this is the characteristic equation. This is the characteristic equation. So what is the characteristic equation? Now the characteristic equation, which is nothing but s power 5 plus 8s power 4 plus 3s cube plus 2s square plus 5s plus k equal to 0. Now this is the characteristic equation of order 5. Now what is the problem you are facing here? If order is 5, order is increased. When order is increases, I don't know the exact poles location and I can take the help of RH criteria to find the system stability. And RH criteria is having a limitation of it does not know the exact poles location. Okay, but for drawing the root locus diagram, I want exact poles location. Now total 5 poles P1, P2, P3, P4, P5. I want exactly the 5 poles location, and this 5 poles locations which is a function of system gain k. These are the 5 poles location and these 5 are which should be a function of system gain k. For the problem for us is it is difficult to find the 5 poles location and that location which is a function of system gain k. So it is difficult for us to draw the root locus diagram because it is difficult to find the exact the poles location. So how can I draw the root locus diagram, which is the movement of the closed loop pole? The root locus diagram is a movement of the closed loop pole when the system gain k is varied from 0 to infinity. But here the pole's location is difficult to find, and that too a function of system gain k, and it is difficult to find the difficult to draw the root locus diagram. This is the problem which we are faced when order is increased. So for higher order characteristic equations, for higher order closed loop control systems, it is difficult for us to draw the root locus diagram. So you want to find an alternate solution for that. Okay, you want to find an alternate solution. Now that alternate solution we will find. Now see how I can find the alternate solution. Now one important point you want to keep in your mind, the root locus is nothing but movement of the closed loop pole. Is it right or no? The root locus is nothing but movement of the closed loop pole. The closed loop pole movement is nothing but the root locus diagram, and this is the direction of the movement of the closed loop pole. Now the root locus diagram starts with k equal to 0 and the root locus diagram ends with k equal to infinity. The root locus diagram starts with closed loop pole and the root locus diagram ends with closed loop pole. Everywhere I need a closed loop pole, am I not? Ultimately, everywhere we need a closed loop pole. Starting closed loop pole, ending closed loop pole, everywhere I want a closed loop pole. So that closed loop pole movement is nothing but the root locus diagram. But here the problem is difficult to draw the root locus diagram because it is difficult to find the pole's location. So how we can overcome that particular situation? Okay, we will see. So I will take a small example. G of s which is equal to k by s, G of s which is equal to k by s. Now this is the open loop control system and this is the open loop pole. Open loop pole is at origin. This is the open loop control system transfer function and this is the open loop pole is available at origin. Now see here. Now the characteristic equation. Now the characteristic equation 1 plus G of s equal to 0. Therefore 1 plus k by s is equal to 0. S plus k equal to 0. S equal to minus k. Now this is the closed loop pole which is a function of system gain k. This is the closed loop pole, right? Now where is the closed loop pole? The closed loop pole is at minus k. Now I am asking one question. The characteristic equation root is nothing but closed loop pole. Now when system gain k equal to 0, when system gain k equal to 0, where is closed loop pole? Closed loop pole is at origin. When system gain k equal to 0, closed loop pole is at origin. Now I am asking one question. Now when k equal to 0, closed loop pole is at origin. Is it right or not? When k equal to 0, closed loop pole is at origin. Now will be exactly same as that of its corresponding open loop pole or not? This is the open loop control system. See the student. This is the open loop control system and this is the corresponding closed loop control system. If this is the closed loop control system and this is its corresponding open loop control system. Now the closed loop pole is at origin when k equal to 0 and its corresponding open loop pole will be also at the same location or not? So now my question is, my point is there any difficult to find the closed loop pole at the starting point? At the starting point is nothing but what? Where k equal to 0 is the starting point of the root locus diagram. At the starting point, is there any problem to find the closed loop pole? Don't worry, instead of closed loop pole, you may take open loop pole. Therefore, when k equal to 0, closed loop pole, when k equal to 0, closed loop pole will be exactly same as that of open loop pole. So, when system gain k equal to 0, the closed loop pole will be exactly same as that of open loop pole. So, is there any problem with identifying the closed loop pole at the starting stage? Then you choose with open loop pole, because when k equals 0, open loop pole will be exactly same as that of closed loop pole. Therefore, the root locus diagram starts with k equal to 0. The root locus diagram starts with closed loop pole. But if it is difficult, you may start with open loop pole. Both are same when k equal to 0. The root locus diagram starts with open loop pole. When k equals 0, open loop pole equal to closed loop pole. Understand or not? Starting, this is the starting point. This is the starting point of the root locus diagram. You may start with the open loop pole, because when k equals 0, open loop pole will be exactly same as that of closed loop pole. Sir, if I know starting it is enough? No, I want ending also. Then I can have a link between starting point and ending point. So ending also you can easily identify. Now first you note down this. Okay. Now students, we will find ending also. Now let us take another example. Now g of s equal to k into s plus 1 by s plus 2. This is the open loop transfer function. Open loop 0 is at minus 1. Open loop pole is at minus 2. Now the characteristic equation. Now the characteristic equation is 1 plus g of s equals 0. S plus 2 plus k into s plus 1 equal to 0. Therefore, s plus 2 plus ks plus k equal to 0. Therefore, if I take s as a common, 1 plus k plus 2 plus k equal to 0. Therefore, s equal to minus of 2 plus k by 1 plus k. This is the closed loop pole, which is a function of system gain k. Now see here, can I write like this? Yes, which is equal to minus 2 by k plus 1 divided by 1 by k plus 1. I just take a k as a common here. The numerator and denominator, if I take k as a common. So now see here, now this is yes. So when system gain k equal to ending, I want ending point, right? Now when system gain k equal to infinity, when k equal to infinity, now this is the closed loop pole location. Now where is the closed loop pole? Now the closed loop pole, which is equal to something by 0, something by infinity, this is 0, minus 1 by, this is 0, 1, which is equal to minus 1. Which means that when k equal to infinity, now you can understand students, when k equal to infinity, the closed loop pole, which is equal to minus 1, which is exactly its equivalent, this is the open loop 0 or not? This is the open loop 0 and open loop pole in the open loop control system. Now if you substitute k equal to infinity, now your closed loop pole, which is equal to minus 1, will be exactly same as that of a open loop 0 or not? Will be exactly same as that of open loop 0. What is the meaning of that? Now what you can understand, I want the ending point now. Ending point, destination point. ending point. Now the ending point is at k equal to infinity. When k equal to infinity, actually I want a closed loop pole. I want a closed loop pole, but it is difficult for me to identify the closed loop pole. Then instead of that closed loop pole, you may take directly, instead of this closed loop pole, you may take directly the open loop 0. You may take directly the open loop 0, because the open loop 0 will be exactly same as that of closed loop pole. The open loop 0 will be exactly same as that of closed loop pole. Now this is valid only in the presence of system gain k. When k equal to infinity, the open loop pole, open loop 0 will be same as that of closed loop pole. Therefore, now the ending point, is there any difficult to find the closed loop pole? You may use the open loop 0. Therefore, the root locus diagram ends with k equal to infinity. The root locus diagram ends with closed loop pole, but it is difficult to identify the closed loop pole. Now we may use open loop 0. Therefore, the root locus diagram ends with open loop 0. The root locus diagram ends with open loop 0, and the root locus diagram starts with open loop pole. Understand or not? So what we can understand? So we can understand that we can take a open loop control system and we will try to draw the root locus diagram, which is the movement of closed loop pole. Don't confuse students. If you take a open loop transfer function, but that is, you are drawing a diagram with respect to system gain k in the presence of system gain k, so it is totally deals with the closed loop behavior only, closed loop control system only. So you are taking a open loop control system, but you want to draw the root locus diagram, because now there is a mediator. That mediator is nothing but system gain k. And one more point also I am saying, if there is no system gain k in between the open loop control system and closed loop control system, now all these definitions are invalid. Understand or not? So that's what I am saying. The root locus diagram don't say moment of closed loop pole. The root locus diagram is nothing but the moment of the closed loop pole when the system gain k is varied from 0 to infinity. Therefore, this point, which is very, very important. So the root locus diagram starts with open loop pole and the root locus diagram ends with open loop 0. Understand or not? Okay, note on this. So now finally, I think you have some alternate solution for that. Is there any problem in the closed loop? Then you may take directly the open loop transfer function and we will try to draw the root locus diagram. Okay. So the root locus diagram is starts with open loop pole and the root locus diagram is ends with open loop 0, but the starting point is k equal to 0. Open loop pole will be exactly same as that of closed loop pole. Ending point is at k equal to infinity. Open loop 0 is exactly equal to closed loop pole. So the derivation part also will cover. Okay. Now I just give. Now this is the positive real axis. This is the negative real axis. This is the positive imaginary axis. This is the negative imaginary axis. This is explained, we already know that. Okay. Now before that, you know this one. Now this is 0 degrees, this is plus 90 degrees, this is plus 180 degrees, this is plus 270 degrees. Now in this clockwise direction, in this anti-clockwise direction, this is the anti-clockwise direction, angles are, now in this anti-clockwise direction, the angles are positive, 0, plus 90, plus 180, plus 270 and so on. Now this is 0 degrees, minus 90 degrees, minus 180 degrees, minus 270 degrees, minus 360 degrees. Now this is, see here, this is the clockwise direction. This is the clockwise direction. Angles are negative. Okay. Now this is the clockwise direction. The angles are negative, and this is the anti-clockwise direction. The angles are positive. Okay. That is a basic concept. You already know that. Okay. So where is 45? Where is 90? That is important now. So you can easily understand. Now clockwise direction angles are negative, and anti-clockwise direction angles are positive. So by keeping this particular points in your mind, then I am asking one small question. Now this is first quadrant. This is the first quadrant. Now can I write like this? S plus 1. Now which is nothing but S plus 1, which is nothing but, if I replace S equal j omega, 1 plus j omega, positive real part and positive imaginary part. Positive real part, positive imaginary part. What is the angle? The angle is plus, because this is numerator is plus tan inverse imaginary part by real part. Is it right or not? Yes. Now similarly, now this is the fourth quadrant, plus minus. Now can I write like this, which is nothing but, now 1 minus S, which is nothing but 1 minus j omega. 1 minus j omega, now which is nothing but, now this is numerator positive only, therefore tan inverse imaginary part by real part. Tan inverse imaginary part by real part, therefore which is nothing but minus tan inverse omega. Now this is the angle, okay, minus tan inverse omega. Now this is in the fourth quadrant. Now I am asking, now you tell me what is the angle here. Now in the second quadrant, now see here, so can I write like this? This is S minus 1, which is nothing but minus 1 plus j omega, but here this real part is negative. Remember this one. But all these real parts are positive. When this real part is positive, actually this reference angle is 0 degrees or plus 360 degrees. 0 degrees or plus or minus 360 degrees, right, in the clockwise or anti-clockwise direction. But now this is the real part negative. Now this is nothing but plus 180 degrees, or this is nothing but minus 180 degrees. Okay, this is plus or minus 180 degrees. Now this is the real part, then this is the real part which is nothing but minus 1. This is the real part which is minus 1. Now see here, now whenever the real part is negative, now this is not a reference angle of 0 degrees. This is 180 degrees. Therefore, now this is 180 degrees plus or minus, because plus 180 and minus 180 same. Plus 180 degrees plus tan inverse imaginary part by real part. Therefore, the angle is 180 degrees minus tan inverse omega. Therefore, now students, you just remember one important point. When the real part is negative, it may be in the second coordinate and the third coordinate, because this is the negative real part. Therefore, the angle calculations are made reference with respect to 180 degrees. Okay, that point you have to remember. Now otherwise all the analysis will go wrong. Now see here, this is the third quadrant. Here is also negative real part. So minus s minus 1. So can I write like this? Now this is nothing but minus 1 minus j omega. Therefore, now this is again the real part is negative. If the real part is negative, the angle calculations are 180 degrees plus tan inverse. Imaginary part is minus omega, real part is minus 1. Therefore, the phase angle is 180 degrees plus tan inverse omega. 180 degrees plus tan inverse omega. Now this is 180 degrees plus tan inverse omega. Now this is the phase angle 180 degrees plus tan inverse omega. Now this is the second coordinate and this is the third quadrant. And this is the first coordinate and this is the fourth quadrant. Now see here. Now these are the phase angles calculations which are very important. But don't remember second coordinate, third coordinate, all these things. Now the real part is negative, then you take a reference angle of 180 degrees. If the real part is positive, then you go for the normal calculations. Okay. Now this is very important because angles are goes wrong entirely, analysis will be goes wrong. Now you just take this one. Okay. This is a basic concept only. Just I want to recollect you because now the angles will play the important role. Magnitude is no problem because square root of real part square plus imaginary part square. Angle is important. Whether in the angle in the denominator, you can take angle of sine of minus because theta 1 divided by theta 2 is nothing but theta 1 minus theta 2. Now, so now I want to find one important point now. What should be the link between a open loop and closed loop? Because now I am taking a open loop transfer function to draw the root locus diagram. I am taking a open loop transfer function to draw the root locus diagram. What is the link between open loop and closed loop control system? Okay. Now see here, our final ultimate answer, I want to do the closed loop control system analysis. I want to do the stability or anything of closed loop control system. That is available in the, that is possible with the help of closed loop poles. These closed loop poles are available directly in the characteristic equation. What is the characteristic equation? 1 plus g of s equal to 0. Therefore, g of s which is equal to minus 1, real part, imaginary part is 0. So this is the characteristic equation. The characteristic equation consisting of closed loop poles. The closed loop poles will give the closed loop control system behavior or closed loop control system stability. But that is here we are facing a problem when order is increases. In order is increases, it is difficult for us to find the analysis of the closed loop control system. That's what we are searching as any alternate methods for finding the open loop control system and closed loop control system and link. Okay. Now therefore, I want to take the first link. The first link is nothing but, you just see here, I just take a open loop transfer function. I just take a open loop transfer function. We are taking a open loop transfer function and we are measuring the angles of open loop transfer function. What I am doing? I just find the angles of open loop transfer function. If these angles of an open loop transfer function which is exactly equal to plus or minus 180 degrees. Now you ask a question, sir, why it is plus or minus 180 degrees? Why you concentrate on not, plus or minus 180 degrees? Why you are not talking about 90 degrees or 30 degrees, 40 degrees? Why it is only plus or minus 180 degrees? Because now see here, g of s which is equal to minus 1 plus j0. This is the characteristic equation. Now this is the real part. Now the real part is negative. Now how we are measuring the angles? Angles are plus or minus 180 degrees plus tan inverse imaginary part by real part. Therefore, plus or minus 180 degrees plus tan inverse 0 is 0 degrees. Therefore, angle of open loop transfer function. Now the students, one important point, if you find the angles of the open loop transfer function and those angles, if you are taking a reference of plus or minus 180 degrees, reference of plus or minus 180 degrees, it is not the open loop control system behavior, it is the closed loop control system behavior, because characteristic equation g of s equal minus 1 means 1 plus g of s equal 0. Characteristic equation, it deals with only closed loop poles. It is the analysis of closed loop control system. But this is based on angles. Okay, this is based on angles. Therefore, this condition is called as angle condition. A small change here, angle of g of s which is equal to 2q plus 1 into plus or minus 180 degrees. Why? Because if q equal to 0, this is 1 into plus or minus 180 degrees. If q equal to 1, 3 into plus or minus 180 degrees. If q equal to 2, 5 into plus or minus 180 degrees, all are same. 1 into plus or minus 180 degrees, or 3 into plus or minus 180 degrees, or 5 into plus or minus 180 degrees, all odd multiples of plus or minus 180 degrees will be at the same location. Therefore, this is nothing but an angle condition. This is the angle condition, which is an odd multiples of plus or minus 180 degrees. If odd multiples of plus or minus 180 degrees is the angle of open loop transfer function, then that is not a open loop control system behavior. That is the behavior of closed loop control system. Now this condition is called as angle condition. Now the second one is, now g of s which is equal to minus 1 plus j0. Now I am taking magnitude of the open loop transfer function. The magnitude of the open loop transfer function by equating real part square plus imaginary part square. Therefore, the magnitude of the open loop transfer function is exactly equal to 1. If the magnitude of the open loop transfer function by making exactly equal to 1, then that is not the open loop control system behavior. That is the behavior of the closed loop control system, because it is characteristic equation. It deals with closed loop pole. Now this condition is called as magnitude condition. This condition is called as magnitude condition. That's what I am saying. No magnitude condition, no other condition, only one condition. That is nothing but the angle condition. If the angle condition is satisfied, students, if the angle condition is satisfied, it is nothing but a characteristic equation. If the angle condition is satisfied, and automatically the magnitude condition is satisfied. And let us check another question also here. Sir, this angle g of s is not equal to plus or minus 180 degrees, sir. It is not a odd multiples of plus or minus 180 degrees, sir. If it is not an odd multiples of plus or minus 180 degrees, now the students, it is not g of s equal to minus 1. If it is not g of s is not equal to minus 1, it is not a characteristic equation. It is not a closed loop pole, and it is not the behavior of the closed loop control system. Understand not? Now this is the another way to check a open loop and closed loop control system relation. Now is nothing but the magnitude condition. And another one is and another one is now see here, now this is g of s which is equal to -1 plus j0. Therefore the open loop control system transfer function g of s with respect to reference point is -1 comma 0, real part, imaginary, -1 comma 0 reference point. If the open loop control system transfer function is studying with respect to x comma y point, no, 3 comma 4 point, no, 5 comma 6 point, no. Now the open loop control system transfer function is studied only with respect to a reference point of -1 comma 0, then only this is nothing but a characteristic equation is a closed loop control system. Now this is another link between open loop control system and closed loop control system. This is called as a point condition. This is called as point condition. This is called as a point condition. Now students, one point I want to say. Sir, then what is the advantages of all these conditions, sir? Now, how you can, why you are saying this is angle condition, this is magnitude condition, and this is point condition. What is the use of this? Now the student, now I want, our topic is a root locus, which is the movement of closed loop pole. Is it right or not? The root locus is the movement of the closed loop pole. But now the students, now in our subject from the root locus diagram onwards, we never use the closed loop control system directly. We always take the open loop control system, but finally we want to do the analysis of a closed loop control system. How can it possible? You are taking a open loop control system, but you are talking about a closed loop control system. Sir, how the link is established between the open loop and closed loop control system? You want to take a open loop control system, but you want to do the complete analysis, complete behavior of the closed loop control system. So that link is nothing but you are going for an angle condition, or you may choose a magnitude condition, or you may choose point condition. Now students, now with your basic knowledge, you tell me what are the remaining topics in our subject. Now we are starting a root locus diagram and Bode plot, polar plot, Nyquist plot. And one important point I want to say is, in all these particular remaining topics of our subject, root locus diagram, Bode plot, polar plot, Nyquist plot, nowhere we are not at all using a closed loop control system directly. For all these topics, we are taking a open loop control system, but each and every topic we want to do the analysis of closed loop control system. So how it is possible? It is possible we are taking a open loop and we are taking a reference as angle condition. We are taking a open loop and we are taking a reference as magnitude condition. We are taking a open loop and we are taking a reference as point condition. If you use any one of these three conditions, it is not the open loop control system analysis, it is the closed loop control system analysis, because it is nothing but a characteristic equation. It is the closed loop poles and it is the closed loop control system analysis. Understand not? This is a very important 3 points throughout our subject, the relation between open loop and closed loop. Okay, this is the relation between open loop and closed loop. But for drawing the root locus diagram, which we already decided, now what is the how the root locus diagram is starting and how the root locus diagram is ending. That is already over. But anywhere there is a possibility of finding the closed loop control system, use these 3 points and you can easily overcome that particular problem what we are faced. Understand or not? So this is the points which are very useful to judge that is a closed loop control system or not. First you just take this one. Now how you can utilize this? Now where we can utilize this, right? How it is useful while drawing the root locus diagram, also we will see. Now I just take one small question such that you can easily understand this. Okay. Now I just take one small example. Now he is giving one trans function. Now g of s, which is equal to k by s into s plus 2 into s plus 4. Now this is the open loop control system transfer function. This is the open loop control system transfer function. And this is the open loop control system transfer function which is given to you, and he is asking identify s equal to -1 and s equal to -3 is the point which lies on root locus branches or not. Which lies on root locus branches or not. What is he saying? Now the given transfer function is given k by s into s plus 2 into s plus 4. This is the open loop transfer function, and he is saying that these points are available in the root locus branches or not. Now first of all you want to know that what is the root locus branch? The root locus branch is nothing but a moment of closed loop pole. The root locus branch is nothing but moment of closed loop pole, and this is the open loop transfer function. He is asking this fellow belongs to a closed loop pole or not. So I can easily use this angle condition at that particular point. Now see here, if I measure g of s at s equal to -1, which is nothing but k by -1 plus 2 plus 1 -1 plus 4 plus 3. Therefore, which is nothing but k plus j0 minus 3 plus j0. Then if you measure the angle of open loop transfer function at s equal to -1, which is nothing but tan inverse imaginary part by real part. Tan inverse imaginary part by real part. Now here this is the real part is negative. Therefore the angle calculations are 180 degrees plus tan inverse imaginary part by real part. Therefore the angle of open loop transfer function at s equal to -1, which is equal to tan inverse 0 is 0 degrees divided by tan inverse 0 is 0, 0 degrees divided by 180 degrees. Theta 1 divided by theta 2, theta 1 minus theta 2, 0 degrees minus 180 degrees, which is equal to minus 180 degrees. Therefore, the angle of open loop transfer function at this particular point is a minus 180 degrees, is an odd multiples of plus or minus 180 degrees. Therefore, s equal to -1 is lies on root locus branches. Note down this and check the similarly the second one.